I'm not sure there's like an official start signal. How's everyone doing? Good? Not quite awake yet? Or awesome. So today we'll talk about building a high-performance database with Scala, Akka, and Spark based on projects that been working on. My name is Evan Chan. If you forget, my last name is on my shirt, so it's only 4 letters, so it's not hard to remember. I've been using Scala for a long time. Just a show of hands, how many people came to Scala from, say, Java? So it's like a lot of hands. How about Ruby? A few hands. So I came to Scala from Ruby, and I came to Ruby from Python. And if you come to Scala from Ruby, it's actually very easy because Ruby is already a semi-functional language. Well, you got a lot of debate in this room about that, so I won't go there. I have been user and contributor to various big data projects, including Apache Spark for a long time. I used Spark when it was 0.8. Way back, like before most people had heard of it, and it was basically like had just evolved from a research project out of Berkeley, and the configuration of Spark was done by setting system properties, so that those were the good days. And I've done talks at various places, the Spark Summit, Cassandra Summit, and I've linked there if you're interested in looking at blog posts and other stuff like that. So today we'll talk a bit about the database about FiloDB, but a lot of this talk is more, the theme is really more about how do we use the abstractions in Scala to build a big data system. Because that's a lot of us might not be building databases, but a lot of us will be like, we want to know like what parts of Scala to apply, and there's a lot of good lessons. But I'll start out with why build a streaming database. So nowadays, like we're dealing with huge volumes of data, like huge volumes of streams. Right, you're talking about there's a lot of IoT applications. There's a few talks here that I noticed that are about IoT, which is kind of cool. But you can imagine IoT, operational metrics. Like no matter where you look, there's like huge streams of data, and oftentimes nowadays it's really important to deal with real-time and low latency data. The two concepts are slightly different, but essentially you want to get at the data that you're ingesting right away and to answer questions increasingly right away. For example, dashboards, right? Well, it's kind of useless if you get the data and you batch it up and then you serve it like, oftentimes like if it's an hour later, it might be too late, right? And oftentimes we're dealing with flexible schemas, data might change. And in all of these things, we want systems to be as simple as possible. If you've productionized and debugged streaming systems, like those are oftentimes the hardest systems to debug because of the velocity that data is moving. It's not like I run a batch job one time and then, oops, something went wrong. Let me run it again. And it might be OK. But in streaming, it's not OK. You can't even have your systems be down like even 1 minute because you could be losing a lot of data, right? So a general architecture for this stuff kind of looks like this, right? You have events coming in to some message queue, and you have some stream processing layer, and then you have state. And the really interesting question, I guess, for us is what does the state look like? And hopefully, like out of all this, you get happy users. You're serving stuff out of your state. A lot of, so a pretty standard solution that folks use is something like this. Like you use Kafka as the message queue. That needs no explanation. Maybe you use Spark streaming to process it, and then you kind of write small files. Now, why do I write many small files? If you use Spark, then you know that Spark streaming is a micro-batch architecture. So it takes data in small batches, like one batch, one batch, one batch. If you want your things to be real time, you can't spend too long writing these files. Like maybe, I don't know, let's say that you want a 10-second window, right? So now you're writing files that are 10 seconds long. So 10 seconds files are not really that big. So what you see is you end up writing a lot of small files. And it turns out that HDFS doesn't really like having like millions of small files. So, and it's also very inefficient to process. So you end up having to consolidate them. If your data workflow involves data that you might see again, you might have to deduplicate. So after a while, you realize that this becomes a fairly high latency workflow in order to get to a point where you can really like read data efficiently. And the fundamental problem is that there's a big impedance mismatch. It's like trying to fit a circle into a square into the round hole, right? Streaming data and files are fundamentally different abstractions, right? And trying to fit one into the other leads to a lot of pain. So you have Apache Cassandra. I think all of you guys are probably very familiar with it. Cassandra is a distributed key value store, a distributed database, really. It's more than key value store. It's designed for you to write tons of data into it. And you can query data right away. So it fits a lot of the characteristics that we are talking about. So this all sounds really good at a high level. Now, if you work with data at a high enough velocity and scale and volume, you soon discover that just working with Cassandra out of the box has its own pitfalls. Oftentimes, you find that the volume that you're able to write using just the native APIs is not quite what you need. So you end up having to massage data in order to make it really work for large volumes. The other thing is that queries have to be very simple. They can be a little bit more than key lookups. You can do like range lookups. But essentially, it works best if you read from what is called a partition, essentially one node or one thing at a time. Now, you can change that. You can add Spark. And there's a lot of stuff that folks have done. I'll point to one of my friends here, Russ, that works at DataStax, has done a lot of great work on making Spark work with Cassandra. So that allows you to do flexible queries. But you make some trade-offs. You get very flexible queries, but then you might not be able to do a lot of them at the same time, and they might be higher latency. Right? So out of all these needs is why we wrote FiloDB to be a streaming solution that can ingest at very big volume and also answer low latency queries quickly. Although I'm not going to be talking that much about the project itself. It is open source. You can look on the website. But the idea is that you can ingest stuff and be able to meet different needs going to dashboards. For dashboards, typically, like you have a lot of users running really quick queries, and as far as for ad hoc and other needs, which are fit more traditional Spark, where you need to run like only a few of them, but they are like much more complex. So we'll come back to this. But what I want to focus on, though, is that we built this stack of FiloDB Spark based on 100% a reactive stack. So this is all of the code is in Scala, which is I'm proud of that fact. And we use the Akka cluster extensively. Spark is part of it, important part of it. We're increasingly getting into using reactive streams. I'll be talking about that a bit. And we use futures, and part of the talk will be about what parts are used where. We use type-safe config for our configuration, and there's other random libraries that I'll point out that I think have been very useful to us. Even the highest performance parts, and I'm quite proud of this fact, the parts that have to run within 1 nanosecond are run in Scala. So using Scala and Akka and Spark for database. So first of all, why use Scala and Akka? So I would say that a big part of it is that we really get a lot of the right abstractions. And some of these, not all of these are built into Scala. Like Akka is a library, obviously. But I think if you combine the whole ecosystem, you get a lot of really useful abstractions. You get streams, parallel reactive streams. You have futures. You have the actor system. You have distribution. You have a lot of important components that you can combine and pick. It's almost like with ecosystem so big that we have to actually pick the right ones, which is a discipline, right? Some of the properties of frameworks like Akka are critical for all systems, but particularly for databases, like failure handling, being able to recover and be resilient all the time. And of course, all the pattern matching and type safety, I think, is actually quite crucial. You never get stuff right the first time. So being able to refactor fearlessly is, I think, one of the best reasons to use Scala. Like when I have to refactor stuff, I don't really think about, oh, you know, like in Ruby, am I going to get a method not found error when I run a job? And like 2 hours later into a Hadoop job, I might get this like funny. Once upon a time, I actually had to run Hadoop jobs in Ruby. So anyway. There's quite a few Scala big data projects. Like obviously everyone knows Spark. You guys might not all know GeoMesa. It's a really interesting project out of the Eclipse Foundation. I forgot exactly who produces it, but basically it's a geo. It's for geodata, and you can run geoqueries on it, which is really neat. Someone's written. I think these came out of Comcast. I think. There's an Akka time series database called Cronus. There's a distributed key value store called Sirius. Oh, sorry, Sirius comes out of Comcast, I think. So, so three big abstractions: actors, futures, and observables are what we use for reactive streams. And so when you use it, in what parts? So here's what one FiloDB node might look like. At the very top, we have a couple actors. And you can think of that the data that comes in the system, as well as commands and user commands, come in through a single coordinator actor at the top of the chain. So everything comes in through there and gets routed to different things. So you can think of there are underlying actors that represent that handle ingestion for one particular, what we call a data set. So just like in Spark, you have different data sets are basically different pieces of data with a single schema, right? Like a table. So you might have different actors for handling ingestion for different data sets. And we might have actors for handling querying and so forth. And below that layer, we would have more low-level constructs that are useful for accumulating records in memory, organizing them, flushing them to disk in a more optimized columnar fashion, and then they get written to a column store. So what you see is that we can organize this functionality in different groups. At the very top, you can see that Akka and actors are used because the top layers have to do a lot of coordination. And we would use futures and observables for the lower layers where type safety and back pressure and other things become more important. So use actors for basically external APIs, for doing asynchronous messaging to and from clients, request response, other things like that, as well as for cluster and distributed state management. So that is a pretty good use of actors, in my opinion. And then we use futures and observables for core I/O, for doing data processing and ingestion, maintaining type safety. The actor API is it's basically like you can ingest messages of any type, so it's a little bit not as safe. And for doing data flows with back pressure. So an example of this is that for actions that are clearly single actions, then that maps very well to futures. For example, like I have an example like drop dataset is one API example, right? It's an action that you do one time, you get a result. If you get an error that happens when you execute it, then you also get an error back from the future. So this maps very well to a future because futures run one time and then you get back this response, right? Now, in the when we originally wrote this, there was actually a lot of the reactive streams landscape was really like nascent. It was just starting out. And so we did a lot of things with futures, including things that probably should not have. I give an example of an append of a write API. But a lot of these things we've started to migrate into using reactive streams. So out of curiosity, how many folks are using reactive streams in your stuff. So few, I don't know, maybe 10%-ish or maybe 5%. So you've probably heard a lot about this reactive streams. I think there's other people there's a talk on Akka streams later. The JDK 9, I believe, has a Flow API now. So this is becoming a really hot topic, and with good reason. Well, what are streams? Well, everyone probably knows what an iterator is, right? So an iterator is something that iterates over a sequence of data in a single thread. What streams are is that they are asynchronous streams based on observable sequences. And they are asynchronous, which means that different parts might execute on different threads. And it is designed from the ground up to have back pressure, which is, I think, a really important part. So it's asynchronous, yet so you can have several parts that might be executing in parallel, but at the end of the day, all of them actually conform to a back pressure API. So you know that when you produce, a producer will wait for the downstream to be ready. And that's built in. Now, Monix is a particular a reactive streams library that has been built from the ground up for Scala. So it interacts very well with Scala. It has integration with a lot of things in the Scala ecosystem, including futures and some other type level projects like CATs and other things like that. Before, we were using things like future iterator, which really doesn't work that well. It's not, that's not asynchronous, really. It just happens to give you an API that returns something in the future. But streams are much better because if you start thinking about things, one example is, say reading data, right? Now, it might seem to you that if you have a standard app, reading data might be something that you think of as a future. Like basically, you get some answer in the future. But in the database, basically, reads have, you want things to be streamed. Because if, let's say you're reading a few rows, then it probably doesn't matter, right? If you're reading, say, 100 million rows, on the other hand, you don't want to wait for all that to be done to get an answer back. What you want is to have a streaming API so that you start getting data back and in sets, right, in parts. Then somebody else can work on that, like say Spark, and do some processing on it while you fetch more data. And then the back pressure comes in so that if the processing is slow, then you don't push more data than the downstream can handle. So in this example, we're returning an observable, and what happens is that each part, so scan partitions, partitions are kind of like groups of objects in FiloDB. And you can think of, in an IoT application, it might be like, say, each entity or each, I don't know, whatever, machine. And so you have one method that might go through and return partitions. And then what we do is we do a flat map. And then for each partition, we might go to disk and read this from, say, Cassandra or something. And the really nice thing about what Reactive Streams gives us is that the read partition chunks could actually be, it is actually asynchronous. It could issue parallel reads to disk. And what Monix allows us to do is allows us to merge those results back in a way that still gives us back pressure. And it's very easy to merge them. The flat map will turn each partition into a sequence. Normally, you think of Scala collections, flat map takes one object, and this all happens in a single thread. But in this case, the flat map, the things that underneath the flat map could be running asynchronously, and this makes sure that it all works. So that way we get, we can control the parallelism and get, fairly good performance. And we still get a really nice compact representation. We can use scan and collect and do things with the results. Another area is in terms of ingestion. So what we get with Monix, the first thing that you notice is that we have a merge. So we're able to merge multiple streams together. One stream is a lot faster than the other in this case, but they still get interleaved correctly with back pressure. And then you notice another thing which is really interesting called map async. So what map async does is it will take objects off of a stream and it can fork them into tasks which run in parallel. Well, in this case, num-parallel flushes is what controls the number of parallel things that are happening. So if say it's 8 or something, that means I can have 8 tasks that are run. So I can take 8 objects from the stream and run them in parallel. And if one finishes, it will take another one off the stream. So this is a fairly powerful abstraction. You can control the parallelism really well, but the whole thing is still back pressured. And I know that if the flushes slow down, let's say that all 8 of them slow down, then it will stop processing upstream more data that comes in. So this is a really important property to have in data flows. Monix in particular is designed to be like really fast, like to the metal, and give you really fine control over parallelism and other things like that, which is one reason why we use it. And the other thing that you notice is that there's also error recovery. There's a recover in there, right? OK, so I'm going to move on a little bit to talking about mixing in Akka cluster and Spark, which is fairly interesting. You might wonder why we're doing this. I'll explain this in 1 second. But so in Spark, you have an executor thread, a driver thread that runs your application. And then you have executors, right? So bear with me for a minute. Let's say that you have an actor and a driver that can respond to membership events in Akka cluster. So what happens is that when an executor comes up, it will send an event to this actor and the driver, and it will know about membership changes. So it knows that an executor is coming up. And in this case, executor 1 comes up, and then executor 2 will come up, and then you get another member up event. And then the node cluster actor knows that another one has come up. Now, this is pretty interesting, and it's pretty non-standard. How is this useful? So an example is that is for sending commands. So this is something that, because we have a lot of state in our data processing layer, we can do interesting things like tell all of the workers to flush the data. So this is something that is like basically it doesn't fit within the Spark abstraction, because Spark is just for processing data. So in this way, we can send asynchronous commands. We can tell each one to flush, and then this one will flush the data memory to disk. Why is this important? Because for certain, like let's say that we're ingesting a whole batch of data in Spark. At the end of it, we might still have state remaining in all the executors. We want to flush that and ensure that data gets written so that you can read it properly, right? So, so I already talked about basically async messaging. That's one really interesting use case. The other interesting use case of why we integrate Akka cluster into Spark is for stickiness. So Spark is not inherently designed for sticky operations, meaning that when you get each new batch of data, let's say I'm sorting it. Well, with each new batch, the range of data that gets sorted to each worker is going to be slightly different, because each set of data is different, right? But for some of the processing that we do, for example, we encode data into a columnar format. You really want the same key to go to the same machine again and again. So you need something called stickiness. Implementing stickiness is very non-trivial. Like I've done it several different ways in Spark. What we decided to do is to route these incoming records. Maybe this will be a better explanation. So basically, you can imagine that each executor will get some source rows. What we do is that we have an actor that can actually called a row source that can actually take this data and route it to the right another node. And routing is not the same as sorting. Sorting means that you actually have to take every record, like say you have 100 million records. You have to sort all of them by a certain order. Routing just simply means like I'm not sorting it within each bucket, but I'm just sending each one to the right destination. And the really nice property about routing is that one is that I don't need to wait for sorting to happen. So that saves a huge amount of latency when you ingest, and it allows me to act on stuff right away. So that's another use. What we do is that you see there's a node cluster actor that keeps track of membership. That is used for keeping track of the routing assignments. So it knows what is the range of input keys and to route to each thing, essentially like a token range. And so we can use that to route in real time to different parts. One really nice property about, OK, so you notice in this diagram, everything this is happening is in one process. The executor is one process. But let's say that I want to change my architecture around and maybe separate out part of this to like a different process, right? Well, the brilliant thing about Akka is that you can basically do that without changing, basically without changing code. So I can remove part of this, like let's say I want this to be a separate process because it has better performance characteristics, it's better GC, whatever. You can do that. For actors, when you send a message across, it uses what is called an actor ref. It's a reference, which can be local, remote. From the programming API, it doesn't matter. So the really nice thing is that you can reconfigure your architecture, and your code remains pretty much exactly the same, which is really, really nice. So you have to test all this stuff, right? How do you test it? Well, Akka has a really nice testing kit called multi-JVM. And it actually is an SVD plugin. It allows you to spin up multiple processes. And it has things like barriers so that you can wait until all your tests are at a certain point together to execute things. And you can even test that. You can even simulate network conditions like inject faults and things like that. So it's a really useful test kit. There's another library we use, which is really cool, called Kamon. I don't know if anybody's heard of it. But Kamon is basically like metrics for the reactive stack. It gives you the ability to trace as well as have metrics on actors and things. I'll talk about tracing a little bit. What tracing means is that let's say you have something that is broken up into multiple asynchronous segments. This is this is part of the write workflow. So that something like write chunks and write indices might happen in parallel. They're both futures. Even within write chunks, you see a future traverse, so it might be doing multiple things in parallel. So what the tracing allows you to do is allows you to tell how much time is spent in the first part, or in one part, how much time is spent in another part. It will actually measure how long things take. It doesn't do this for every single invocation because that would be expensive. So you can have a sampling rate. And you might sample, say, every 1,000 invocations or whatever. And it will dump this data out and allow you to see it, which is super useful for debugging and for performance things. And it has a metrics system that, like I said, integrates natively with Akka actors, with Akka HTTP, and other things like that. And the histograms use HDR histogram, which is a really good library for measuring precise latencies. For validation, we use something called Scalactic. People probably have not heard this much, but it is actually built into Scala tests. And it allows you to do, if you look at this for comprehension, this is when we validate schemas. There's a lot of different steps to it. So you can actually compose this really well, where if the first step, get computed columns, fails, then it will fail with. So the API looks kind of like that. It looks like you get a result back or something else, which I think is quite readable. So it will give you back this error, and it will keep going until it's validated every single thing. So it's a really neat library, and you can compose these things fairly easily. And the last part of the talk, I'm going to talk about machine speed Scala. This is really neat, like how to get things to run really, really fast. A lot of times, people tend to write these parts in Java, but I'll tell you that you can definitely write anything that runs as fast as Java and Scala. It's just maybe a little bit more work, and won't look like the Scala that you love necessarily. How do you go really, really fast? Well, you try to avoid some things as much as possible. Try not to serialize things. You try not to allocate things, which sounds like impossible. And you try not to copy things. Yeah. So our abstractions under the hood, our columnar format can do can do billions of items, single-threaded. If we go through Spark, it's a little slower because Spark has a row abstraction that slows things down a little bit, but it's still, in the grand scheme of things, extremely fast. This is the repo underneath that we use. You can think of it, let's see, what's the best way to think of it? You can think of it as like a Scala vector or an immutable sequence that you can read back extremely quickly, and which does not need to be serialized. Basically, when you create it, it is already in a binary format, which means that it can live off heap for GC-less memory management. And you can access it linearly or randomly, and it is also very compact because it uses columnar encoding techniques. We use JMX for testing performance. So this is an example of the loop that we use for testing. It is a for loop. Notice that there's an optimized keyword. There's a special Scala library called Scalactic. It might be renamed now, but this is the macro that we write a for loop into a while loop. So what we're doing is a really tight loop that all we're doing is pulling one element at a time and summing it. And so this runs at 2 billion adds a second in a single thread, right? So who said Scala cannot be really fast? And a lot of the magic for getting this kind of performance is using something called JVM Inlining. And basically, the trick is to have a lot of really, really small methods. So at the top, the apply method gets out an individual value. Let's say that this is using differential encoding, so it might add something to a base value. Underneath the hood, another layer, we might have another thing, like really small method that basically you have a different method for different types of number of bits, for example. Like there's one for 32 bits, there's another one that works with 8-bit values, and everything gets converted to an int at the end. And then at the lowest level, you have something that works at a very low level to get out the actual ints from the machine. And this is using sun misc unsafe, which is basically translates directly to a machine read operation. So the JVM will, as long as it is under a certain number of bytes, or sorry, not bytes, but yeah, a certain number of JVM opcodes, basically the JVM can inline these method calls into a single runtime, which makes it really, really fast, but still gives you a way to not copy and paste much code. You can still have some nice abstractions. Doing a final def is very important because that avoids virtual method dispatch. That lets the JVM know that there's really only one instance of this method, and so that gives it further optimization. So it is still possible to use traits with this really high performance thing. The other example of doing machine C Scala I'll go into is something that we call a binary record. So in most applications, you actually know what your domain classes are, like you would model them as case classes. In a database, we have a tougher problem in that we have to support flexible schemas. So at runtime, someone can define, like say tomorrow, someone has a new type of data they want to ingest, right? So I would have to define that dynamically, right? I would say, this type of data has like events ID field, and it has a timestamp field, and it has these other 10 fields that are domain specific, but they don't know that ahead of time, right? So we have to deal with flexible schemas, but we still need a record type, something that can hold, say, one record that has these different fields. And we want it to be fast. So this is a fairly difficult problem, right? Like you can think of what generic ways can I do this easily in Scala? Well, there isn't really. I mean, I can use something like a seek of any, for example, right? So that's kind of really slow. It means that everything has to be boxed into an object. And serialization becomes very costly. So the solution that we have is something called a binary record. What it is it's essentially a binary data type. That means the data is already serialized when it's created. But it supports different schemas. And you can extract values with no serialization. And the way you do that is that part of the trick is that we have a special string class, which is a UTF-8 encoded string class. It basically translates it's strings that are already serialized. In the JVM, Java strings are actually all 60-bit characters. This also saves a lot of space over the wire. And once you build a record, it becomes immutable. This sounds a little abstract, but I think if we look at sorting, I think it will become clear why this is a huge benefit. So if you sort something, basically, let's say that you have a standard, like a protobuf record, right? What you need to do is, first of all, you get a protobuf, you need to deserialize it into an object. Once it's deserialized, you have to create a sort key, so that might be another step. And at each step, you have to do an allocation, you have to do some deserialization and some work. Then once you have a sort key in memory, then you can actually compare it. And so this might seem like something that is like an obvious way to do things, but when you look at it in depth, you realize just how expensive it is. There's a lot of memory that gets allocated. There's like an incredible amount of code that has to be actually run to even make this happen. With something like binary record, we don't ever deserialize or allocate memory. What we do is, other than actually allocating for the actual binary record itself, like from the network or whatever, what we can do is, for example, that you have a name field and you have a timestamp field. We just compare those directly in memory, and we don't ever allocate anything. So that's the kind of stuff that you can write to get very high performance throughput. Finally, I'll give a shout out to JMX. There's a really good plugin you might want to use, SPD JMX, for micro benchmarking things. In summary, I think Scala and Akka gives you, and the Reactive stack gives you really awesome abstractions and performance. We use Akka. You can use Akka for distribution, for state, for protocols, cluster management. Can use the right tools like reactive streams for type-safe concurrent stream processing. And if you need faster performance than what the standard library gives you, you can also build very fast abstractions yourself with fairly good APIs. Thank you very much. I'd like to thank the whole ecosystem for that. I guess we can have a few questions.
So you said that it's minimum deserialization. That means you have a trade-off that your record is not compact, so you have a larger file size.
So you said so the question was, by minimizing deserialization, do you have a trade-off with record size? I would say actually, in our case, it's not true. So objects actually use a lot more memory because each Java object has to have a minimum header size of 16 bytes. And you need an additional pointer to point at it, which is another 4 to 8 bytes. With the binary record, basically everything is in line. So you don't need to waste the space of additional objects. So it depends on exactly what it is. You can argue that strings are also more compact because we use, say, on average of 8 bytes versus 8 bits instead of 16 bits each. But you can argue that in some cases, it might be slower to process a native UTF-8 string instead of a Java string, which is very highly optimized. But I think the trade-offs are probably worth it.
And the second one for that, you said you are using UTF-8 strings.
Yeah.
Does that allow you to still supporting other languages, non-native, or special characters outside of UTF-8?
I mean, I think basically the UTF-8 strings that are encoded are basically compatible with essentially like C strings. So I would say it gives you more compatibility with other languages. Like, it depends on what you mean by other languages, right? Like, ultimately everything that we're doing runs on the JVM, but if you mean being able to read the data from other languages, I think UTF-8 encoding is actually better for compatibility. It's just not as good in terms of like the special string class we have. It's not going to give you every method that a standard string class does. So it's less compatible from a Java point of view. All right, I'm available for questions. All right, thanks.